Yeah? And some examples were already mentioned. Yeah? Traffic simulations were mentioned. Yeah? These guys can actually be used as ways to provide to people services, which they can use in their daily life in order to make something better. But it's not only people; it's also companies who can benefit from such distributed computational resources. Yeah, they can build service offers way better. Yeah, companies that build machineries, for instance, they can catch the data of all their devices and can transform them again into some higher level information. They can do predictions. They can do when something fails. They can call basically their customer before this machine fails, telling him, hey, it fails tomorrow. Shall we replace it today? Yeah? You can have these use cases if you have the right computational power to calculate these analytics. And for these things, clusters and HPC systems are ideal candidates. Yeah? To take the computational power once it is needed. What I experienced in my work so far is, as I said, I started as an electrical engineer working for companies like Porsche and Nokia, and I left them. Yeah? I left them because I realized that there is a shift. Yeah? There is this shift in parallel programming. It's on the chip and it's in the distributed systems. And I left them to learn actually how to do this, how to leverage this performance. Yeah? And after, I hope that I learned something, I'm back. So I'm now again back with Siemens and I'm working again on embedded systems, where in the smaller scale part, we try to leverage the performance on the chip and amongst individual devices called IoT. Yeah? And in these cases, clusters always show up where analytics are there and so forth. So the performance is the driving part, the applications are the driving part, and I would think that these are the most important things. In order to achieve this, of course, you need to have the right infrastructure. So playing this, I'm not so sure whether playing this exascale game, let the US and China run this game and spend their money on some whatever. It's nice. If it's nice to be the top one in the top 500, it's certainly nice. You get a sheet of paper, you can put that on the wall, and that's nice. But you do not earn something from that. Let's think about better how to build up this infrastructure and what are the applications that shall be supported on this infrastructure, and then also make these infrastructures accessible to students such that they can early start learning how to use that. Because from my view on education, these assets you're going to need, parallel programming assets, are still underrepresented in the curricula of universities. So there shall be a change.
Thank you.
That's it.
I think Daniel said it very beautifully. We spoke about supercomputing going to an extreme height, expensive, and then we spoke about exotic applications that may not touch our daily lives. And people are going to keep questioning, do they touch our daily life? And I think he very well articulated is going to touch our lives definitively. And we should look at building an infrastructure that can support parallel programming. And that's a big question around. But we also have on the panel Siddharth, to whom a lot of people ask around the storage part of it. He's worked with companies like Veritas in past. He's currently working with NetApp. And people say that, hey, if I have an infrastructure, how do I move this data that is agile, the data that can easily reciprocate and still can cost minimal? So Siddharth, some of the thoughts around high-performance computing storage and some of the other thoughts the panels.
Thanks for a nice introduction, and also you make me a little bit more comfortable in the sense that I was feeling. Can you hear me? Yeah. Yeah. So I was feeling a little bit odd man out because everybody is talking about compute. I don't have anything to talk about compute as such. I will talk about what is compute all about. Compute is all about no data. So high performance computing, people get very excited, and there are enough reasons for that, is to how do I make the MIPS or teraflops or whatever, is that more and more higher. And that's what when the people talk about exascale, they talk about exaflops as, it's only compute oriented view. But what is behind the scene is that there were serious limitations from the compute side because it needs to move the data at that similar rate. And data movement was severely restricted by our age-old disk systems at the most, and which were not becoming faster, whereas processors have gone through the roof in their performance, whereas the disk systems are pretty much at the same level. Only we talk about that higher capacity of the disk, but not about the that capability to move bit data faster, right? And memory is becoming faster, so it can take more data, but at a faster rate. But the source of data is not supplying it. So that's where kind of my expertise comes in. That with this new disruptive storage technologies happening in the last 5 years, this is probably unique for this industry, storage industry. It has disrupted the industry in a very significant way because the flash has changed the scenario completely. HPC was the only area where now people are talking about multi-gigabyte per second data transfer, whereas that is becoming common, not very common yet, but it will soon become because of the flash. And now even faster persistent memory is coming. Intel just last year announced 3D cross-point memory, which is even at least 10 to 100 times faster than flash. It's almost like becoming your main memory. So HPC architecture can be leveraged by using this faster memory, and they are all very, very power thrifty. So the power consumption is extremely small in this kind of memory. So you get both the power benefit, which is a big problem in the HPC area, as well as this kind of faster movement of data. And the other trend, which is very interesting that's happening, as our speakers were also mentioning about, that people are not so much talking about HPC in the context of, say, weather modeling or simulation, big simulation. They are there, but there is a big compute or more regular applications are coming up for this data analytics. They are also kind of big data they are called that data intensive computation. That's a new term that's coming up, which is requiring very large amount of data to be moved to the compute farms so that you can do very interesting applications on that, machine learning, artificial intelligence, whatever you have. And particularly in the Indian context, as we go for better and better governance, we have to have this kind of applications built. And so our HPC vision should encompass that what kind of applications we want to build with a large volume of data which are going to be gathered through our various government agencies. We have been computerizing for quite some time, and so we are in a position to have access to a very large amount of data. We should think about how we can generate from those data the appropriate policy decisions, appropriate impact of those policies, those kind of socially powerful, impactful applications. And that should be included in our HPC vision. Okay. And since I have talked about the storage part, but also I would like to say, since it's about HPC, I would like to indicate that there is another trend coming up, which is kind of increasing the computational power significantly more, or people say it is much more infinite, not exponentially higher than what we have today. That's the quantum computing. many nations are investing significantly on quantum computing, as particularly from the quantum cryptography point of view. In fact, in USA, NSA last month announced that they have to go beyond quantum cryptography because they think that's a credible threat to the their national security, because somebody will have access to this quantum computing and they will break all this cryptographic code. So they want to see beyond it. And I would like to see that India at least looks at the possibilities in quantum computing, particularly from the quantum cryptography point of view, keeping in mind our cybersecurity issues.
Siddharth, excellent. Before I got onto the stage, Venki told me that you are on IST, Indian Stretchable Time, not Indian Standard Time. So we're going to actually take benefit of that time, open out the questions for the audience. There have been fantastic, thought-provoking inputs, both from an investment perspective, skill perspective, usage perspective, architecture perspective, use cases perspective. So we'd love to hear questions from your end, and any panelist can take that as an answer. Yes. We would need a microphone on that side, though. Okay, so we'll just let him go by the time. Go ahead.
We heard from the panel on HPC with respect to compute and with respect to storage. Vishal, if you could just throw some color on with respect to the third dimension, which is visualization, that will be helpful.
Oh, absolutely. I think I should allow you to do it, or you want me to answer? Please go ahead. He has been talking about many architectures, so it will be really useful to get your view, because simulating and visualization is a pretty big aspect together.
Yeah, so visualization really is what lets you draw insights from data, right? And I think I would just say that if you have a specific question, I think I can probably do more justice.
No, I'm just,
from the
just at a high level about the trends. So we understand, the data sets are getting larger. So we understand the compute side of it, what it takes to compute, and the volume is getting higher data. So we understand, it is difficult to move that data from, to the compute or compute to the storage. But what are the challenges or what are the trends in the visualization space? Is that what's?
I have a few comments, right? So if you think of a non-traditional part of the computing, like we don't talk about traffic problems and all, think about the movie industries, right? How it's evolving. If you see any of the movies these days, the special effects, so the backend actually run on supercomputers. That uses all kind of platform, and there you need real fast data movement. So the panelists here, what you have been talking about, we need high-end processors, we need high-end graphics card, we need high-end storage with a high bandwidth. That's the backbone of that multi-million-dollar movie industries. Think of the life of Pi. Think of Godzilla. So if you are not aware, the Godzilla, the backend simulations, all the frames by frames, they are developed in ITPL, the motion picture survey office. They have a bunch of engineers working on creating the frames, frame by frame. That's the effect that people don't basically, they don't realize that whatever they're seeing on the movie screen, paying $500 in the IMAX or something, so that's actually HPC.
Hopefully 500 rupees, no dollars.
Yeah,
$500.
500 rupees. Yes, 500 rupees. I was so inclined about talking about dollars that eventually.
And especially with the rupee becoming weaker against dollars. So
yes, I wish. Yeah, I think that's actually what the common man see. So that's the power of HPC.
Actually, the power of visualization also, just to extend on his example, all of us saw this movie, what we pronounce as Avatar, and Americans call Avatar. That 2 hours movie is completely computer generated. Think about this for a minute. One frame.